All right, folks, we are doing integration by substitution. So what I got here is a series of word problems. I got four of them here. So these are all from your textbook. So if you got your textbook handy, you can pull that out. We're going to start with this number 59, population growth. So you got population of a certain city. It's projected to grow at this particular rate over 5 years. All right. So, and they want to know the current population. We know that the current population is 60,000, and we want to know what the population will be 5 years from now. All right. So this is one of those initial value problems. So what we're going to do here is, all right. So here's what we got in our equation. We've got R of t is equal to 401 plus 2t over 24 plus t squared. All right. So now what we're going to do with that is we're going to have to integrate that. So we're just doing our initial value problem. We're using our check downs in there, but we're going to have to use substitution on this one. All right, so I'm going to try to take, since this is my rate, I want to know what my actual population is. I'll call um, I'll just call it capital P of T, population at time T. And that is going to be if I take my rate as a function of T and I integrate it over T like that. All right, so I'm going to say that is equal to my function up here. Now I'm going to do something on the fly here. I am actually going to distribute the 400 through there. That is going to help me out quite a bit. And so I'm going to have this 400 times dt. I am also then going to have 400 times 2t. I will have 800 times t all over 24 plus t squared like that dt. So on the fly, I've made it so I can break it up into two different integrals in here. And the reason I want to do that is that this one's going to be pretty easy to solve. This one's going to require some substitution in there. But all right. So the first integral is going to be basically 400 times t. All right. And I'm going to hold off right now because I'm going to have to do a substitution, but I can pull an 800 out in front of this. So I'm going to have t over 24 plus t squared, like so. All right. And then dt, like this. All right. So this is one of those places where I look and say, oh, wait a second, there's no quotient rule. But one thing I can do is substitution. And what catches my eye in this is that I've got a t squared term down in the basement here. I've got a t up in top. And that is telling me that I am going to let my new variable u, I'm going to make a substitution. We're doing integration by substitution. I'm going to let that equal 24 plus t squared. And what that's going to mean for me is that if I take my derivative du dt, that's going to give me 2t, which means, all right, and here's the big thing, we'll do this in red, is that du is going to be equal to 2t times dt, like that. All right, so, okay, so that I'm going to substitute in there. And so, okay, though, so du is 2t times dt, but wait a second, I got to do one more thing here. That means that dt is equal to du over 2 times t, like that. All right, and you might have actually just do a little rearranging on there. You could get straight to that step right there. This substitution is going to be very, very handy for me. All right, so if I've got my population, I already figured out that this first one is, and did you guys catch that that should have been a t right there? All right, so just notice, you might have noticed that I dropped that when I did my first integral. I said, oh, it's really easy, and it was just so easy that I forgot to put the t in there. All right, so make a note of that. And then, all right, so what do we got here? So I noticed that as I looked up and said, oh, wait a second, that's not right. All right, so now I've got plus 800, right? And I times the integral. I am going to have, okay, so t is going to stay there. Down here, I have got u, like so. All right, and then, so t over u, and then I'm going to put in for dt that's going to be du over 2 times t. Now, this is the really nice thing that's going to happen here, and that is that this t and that t are going to cancel out in there. It's a little bit of light on my thing there. All right, so my population at time t is going to be 400 times t plus 800. Now, the t's are going to cancel. I'm going to bring that 2 out in front, that 1/2 out in front, basically. I'm going to bring that out. That's a constant. The 1/2 can come out, and that's going to cut that in half. All right, and I am going to have du over u. All right, now do we remember that d cabin over cabin is natural log cabin? Uh-huh. All right, so what have I got here? I have got 400t plus 400 natural log of u, and then on here, I didn't give myself a ton of room, but then plus d. Okay, so all right, so that means that my population at times t is going to be equal to 400 times t, right, plus 400 times natural log of u. Well, natural log of u, or u, go back up here, is equal to 24 plus t squared, like so, and then plus whatever that constant of immigration is. All right, I have now got a general expression, but what I need to do now is I need to deal with the initial value problem on this. All right, so let's go back. Let's take a look. And if you got your book handy, definitely have it out. All right, current population is 60,000. All right, so current population, that means t equals 0. So t years from now, well, now is 0. Okay, so current is 60,000. So if I set 60,000, I take this and I evaluate it at t equals 0. Okay, so I've got 0, and then I've got 24. So that is saying that 400 times the natural log of 24 plus c is equal to 60,000, like so. All right, and so then if I do that, I calculate what c ends up being. So if you got your calculator handy, you can pause. And so c is going to be 60,000 minus this other term. This other term's not going to be nice and neat and tidy, but that's all right. So I just went to my calculator, and if I did everything properly, I end up with, I'm actually going to keep, this is going to be a weird thing, but I'm going to keep some digits in here that don't quite make sense, but I'm going, in terms of, decimal place, when you're talking about a population, this is some number that we're adding on. I am going to round off at the end, round off to the nearest person. All right, get that in place. All right, so look at that. I'm going to go to a new piece of paper here and finish the deal on that. All right, so put this over here. And all right, so now we know what C is. And the question is, let's go back to this. All right, the question was, all right, what is the population 5 years from now? And you know what, actually, I can fit that in here. All right, so what is my population at year number 5? That is basically plug and chug. 400 times 5 plus 400 times natural log of 24 plus 25, and then plus this number right here. All right, so I'm going to add that to it, and I'm going to cut to the chase here because you guys can pause, try it out. And what I end up with is approximately, this is going to end up equaling 62,286. Like so. All right, so round off to the nearest person in there. Again, round up, round down, but the projection is 62,000. All right, so let's keep going. Okay, let's go to the problem number, actually, problem number 60 here. We got an oil spill, and it is growing, so it's The radius, now let's be careful here. In this one, R was the rate, and this one, R is a radius. So notice that there's an R prime in there. That's telling you how big the oil spill, the radius of the oil spill is growing as a function of time. All right, so that's how fast it's growing, the radius. All right, and so that is in feet per minute, T is in minutes, and 0 is when this rupture occurred. You've got a tanker that's had a rupture in its hull. And all right, so then the question is, how big is that polluted area going to be after the rupture? 16 minutes later. All right, author gives us a little hint in here and says R of 0 is 0. Okay, so it's starting with no size. All right, so it starts as a point and grows into a circle. Okay, all right, so let's take a look at this. Same kind of problem. All right, so what have we got here? We have got that our rate of change of the radius. Again, R is not the rate in this one. It is the rate of change of the radius. R is the radius, I say. R prime is the rate of change. All right, so what do we got here? 2t plus 4, like this. All right, so the radius is going to be, if I integrate its rate of change with respect to time, like so. All right, and so now looking at this, I'm going to have, again, I've got something I got to deal with in all of this, and I have got square root of 2t plus 4, like this, dt. All right, now I look at this again, got a problem here. The 2t plus 4 is going to be inside a square root, causes me a little trouble. What my eye catches in this one is that this is only t to the first power, and I don't have anything else I would have to cancel out up around in here. So if I just let u equal 2t plus 4, then I am going to end up with, and I'm going to do this, that du is going to be equal to 2 times dt, or in other words, du is going to be 1/2 of dt. Sorry, folks. That's not what I wanted to do. I wanted to do this. All right, du over 2, basically 1/2 of that. So I'm going to rewrite the same thing. Didn't want to do that. All right, so got du equaling 2 dt. And so when I make a substitution for dt into this, my radius as a function of time is going to look like this. And we're going to see that we need to use one of our old tricks, because we've got 1 over the square root of u in here, and I did not write so then I got to put dt. Okay, here we'll do it like this. I can save it like so. There we go. Now I got to have our little differential in there. All right, so the 2 and the 30 will cancel out, and so I'm going to end up with, all right, and so I have got 15, and this should be a du. You guys probably caught that. I hope you did. Then I put a dt in there. I'm supposed to put a du in there. All right, and so then got 15, so the 2 and 30. So I've got du over the square root of u, like so. And now we're going to take advantage of one of our old tricks. I've got square root of u here. So if I go r of t, I am going to have 15, and then that is going to be times the integral of u to the negative 1/2 du. If that does not make sense, stop and think about how this is. It's a square root in the denominator. So not only is it a 1/2, it is a negative as well. All right, now that's something I could do. Okay, so I've got 15. Now this is power rule. So I'm going to take u, and I'm going to add 1 to, its the exponent that's there. So I go -1, add 1, up to 1/2. Like so, -1/2 up to 1/2. Then I'm going to divide by my new exponent, like so. All right, and so then, and my new, so started to put my old exponent. It's telling you exactly what I always tell you guys, don't put your old exponent. All right, this is kind of funny because if I had noticed this, and I did, but I was doing it kind of more brute force, I noticed that if I had kept the 1/2 there, the 1/2 I could have actually used it as part of as part of my solution to my derivative. So notice that I'm going to be right back to having a coefficient of 30. All right, and what did I forget again to do? And that is better add a constant on there. Right, so should actually have a constant there as well. All right, but no harm, no foul, hopefully. And so I've got 30 raised to the u to the 1/2 plus c, but the thing is, this is actually now this is really technically r of u, so let me actually get it back to where it is done in terms of t, because this is actually technically r of u. And so what have I got? I've got u to the 1/2. I'm going to write it as a square root and remind ourselves that that's pretty easy to plug into our calculator, like so. All right, so there is my general expression for any initial conditions. But we are given that at 0 times 0, that the radius itself is 0. Okay, so let's take a look here. Our author was kind here and gave us some numbers that are going to work nicely. So I'm going to have 30 square root of 4. Okay, oops. R of 0 is 30 times square root of 4 plus my constant, and that should equal 0. So let's see here. Oops, solve for my constant. My constant is going to be negative. So 30 times square root of 2. So that's going to be times 2. And so then my constant on here is going to end up being a negative 60, like so. All right, so now I'm going to take that constant and let's see, now I'm going to remind myself. All right, all right, we want 16 minutes. Remember what time we're looking at on this one. All right, so this right here is negative 60. So if I want to get what is my radius at the 16-minute mark, like this, I am going to have, all right, so 30 square root of 2 times 16 plus 4 minus 60, like that. And all right, so notice in here, this is square root of, so this is 32 plus 4. This is square root of 36. This is 6. And then, so this is 30 times 6. That's 180 minus 60. Pause and pull out your calculator. And, oops, started writing the wrong number. It's 180 minus 60. So my radius at my radius at 100 at 16-minute mark is 120. Now, if I want to go, it says how large. Okay, well, it's a circle of radius 120 feet. And if I wanted to, I could go, and this is actually how your author presents the answer. Oops, is that if you want to calculate the area, you would go pi r squared, but as we've talked about in class, pi r squared, pi r round, it's cornbread that are squared. Okay. And so if I go and plug that in, so that's plug and chug, pi times 120 squared. That ends up being, this is actually how your author wants to report it. He puts a pi, he just actually keeps it exactly like so. All right. So, but you can plug and chug on that. It'd just be a smidge more than 3 times that number right there. So a lot of square feet on that one. All right, again, let's keep going. Pause and ponder that one if you want to. And all right, going to go to life expectancy of a female in a particular country. All right. So, all right, so look at that. You've got all right, so you've got it's reminiscent of kind of those growth curves. It's a little bit different, little bit different form for it. But again, we've got something. This really wants you to convince yourself this is basically the same problem. Here, the exponent was 1/2 in the denominator. Here, the exponent is 0.9. These two are essentially the same problem. All right, so we're measuring t in years. T equals 0 is 1900. All right. And we want to get an expression for life expectancy. And then we know that in 1900, life expectancy was just smidge over 50 years. And so we want to say what would happen in 2000 in that particular country. What would be the case for life expectancy for someone born in the year 2000? All right. And all right, so that'd be contemporaries of most people in the class, I would say. All right, put this over here. And all right, so now we've got that our, let's see, our, what we're going to call it, G. There we go. All right, so I'm going to cut a little bit more to the chase on this one as well. You got to get a little bit faster. And so certainly the one nice thing about video is that you can stop and ponder. And so the function itself is going to be, you basically just put the rate inside the integral sign, summation, and I've got 1 plus 1.09 times t. Now, instead of, in the previous problem, it was raised to the 1/2. This is raised to the 0.9 power. And all right, so this is our challenge. Solve this integral. We'll use substitution for it. And then we have an initial value problem. And so then just plug and chug at that point. All right, now looking at this, convince yourself the substitution that I want to make is let u equal, and it's an equal sign, 1 plus 1.09 times t. Again, what catches my eye in here is that I've got this raised with t raised to the first power. I don't have anything I have to cancel out, but that'll be fine because when I do my differential, the t is going to go away in there. So I'll just be left with the dt, not some function of t in front of it. All right. So du is going to be equal to 1.09 times dt, which means that dt is going to be equal to, all right, du over 1.09. And then I am ready to make my substitutions in here. Okay, so again, as usual, we're going to substitute in for u for this 1 plus 1.09 t. We're going to substitute for dt based on this. And so my life expectancy formula is going to look like this. I'll have that 5.45218 divided by u raised to the 0.9 power. All right, then times du or dt, which would be du over 1.09. And really, I should again be technically saying this is what it'll be as a function of u here. All right. So the one thing I'm going to do, remind myself, is wait a second. Okay, so the 5.45218 is going to come out in front. I will have an integral. I will have u, oops, and it would be divided by 1.09. So that, okay, so we pull both of those out. I could do that calculation. I'm going to not do it right on the fly here, but that's plug and chug. But then this is going to be 0.9. That's my exponent. And over du, like so. All right. Okay, so let's take a look here. Looking good. Yep. All right. So now u to the negative 0.9. So my function of u is going to be, all right, so not going to calculate this yet, but I am going to, 1.09. All right, then I am going to have, now this, I got to take u and I got to add 1 to it. All right, so if I add 1 to this, I am going to end up with u raised to the 0.1 power. Okay, added 1. Then I got to divide it by my new exponent. And then this time I'm going to not forget and add my constant on there. All right, so then now what I need to do is now I am ready. So taking a look at this, I've got I'm going to do my calculation in here. I've got 5.4 over something a little more than 1. This is going to get me to around 5, but then I'm going to divide by 0.1. That's going to get me to something that is around 50. So when I do this as a function of time, my function is going to look like this. Keep some digits there. So you see I get something that is around 50. Then I am going to be times u, but u is 1 plus 1.09 t, and then that's going to be raised to 0.1 power, plus whatever my constant is. So again, there's my expression, and I'm ready to do my initial value problem and calculate what c is. And all right, so now let's double back. What was our initial condition on this one? Right. All right, initial condition on this one is that in 1900, 50.02 years. Oh, what a surprise. All right, so, okay. So according to this, then that means, convince yourself, C is 0. And so now the only other thing that I got to do is I got to go in here and I've got to calculate what about in year 2000. All right, so that's going to be 100 years later. And I'm going to cut to the chase on this and say, take 100, plug it into there, calculate on your calculator, and you're basically going to have 50.02 times in here. You'll have 110 raised to the 0.1 power. This is going to give you around 80.04, and that is going to be in years. And so notice that's quite an improvement. Life expectancy here of around 50 years, 100 years later, around 80, presumably nutrition, healthcare, maybe not as maybe no wars or something, but anyway. All right, now got one more to do. We'll wrap it up. All right, so over here. Okay, so last one, similar. All right, this one, a little on the trickier side. So this is actually average height of boys, data collected by pediatricians in there, and so you've got this is the rate at which the average height of male children changes at the rate. Okay, so this is your average height, and this is in inches per year, where the child's height's measured in inches, and t is measured in years. All right, so we want to find average expression for height of boy at year number t in there. All right, and then we are told something. Okay, at birth, 19.4 inches. We want to know, what about an 8-year-old boy? What does that mean? All right, so we got so this is literally a growth curve. It's the growth of people. All right, I chose this one. It's got an exponential in there. We're not going to not let that daunt us. Now, we're going to be taking a derivative. What jumps out at me in terms of how I can get things to cancel is that down here, I've got an expression with e in it. It's squared. But when I take my derivative, if I were to substitute for this, which I'm going to substitute for the 1 plus 2.449 e to the negative 0.3277 t. But when I take my derivative, because that's an e to the x function, that's a natural exponent function. When I take my derivative, I'm going to be left with a factor of that, which is going to allow me to cancel this one out. Right, so that's, again, in your check down. Got to be looking for things like that. All right, so let's see here. We have got, all right, so we've got this function, right? And so now I'm going to do I'm going to be even faster with this one. All right, so I am going to make a substitution right off the bat on this one. I am just going to say, let's let u equal 1 plus 2.449 e to the negative 0.3277 t, like that. All right, so now I'm going to use my chain rule for exponential functions, subject of exam number 4, so that when I take my derivative, du is going to be equal to, the 1 is a constant, that goes away. I'm going to end up with 2.4449 times negative 0.3 in here. So when I'm going to do all this on the fly, because this is going to be the 2.4449 is going to be there. Then I'm going to have e to negative 0.3277 t. Then I'm going to have my final link in the chain, which is going to be this negative 0.3277. All right, so it's going to look like this. All right, coefficient comes along for the ride. Here is my last link in the chain, but I'm just putting it out in front. And then it always kicks back the same function, right? Exponential. Okay. And so, all right. So now looking at that, got our substitution, and I should have a dt at the end. All right. So now this is telling me that dt, a little rearranging in here. Pause and convince yourself this works. Now, oops, this is going to tell me that dt, after I do some rearranging on this, is going to be negative 1.24605 times du, like so. All right, so pop your calculator out and start, convince yourself that you can get to that. Pause if you need to in there. All right, and so now this one I'm going a little bit faster, and so now I'm going to have an integral. My height as a function of u is going to look like this. Right, so it is going to be, all right, so now looking up here, I've got this 52.8706. I'm going to put that out in front. All right, 52.8706 times negative 1.24605. All right, times, now I'm going to have my integral here, and that is going to be basically du over u squared. All right. Go back, convince yourself, do the right substitutions, convince yourself this is what you end up with. Okay? And so there's my integral. All right, this one I can do. And so this one right here, this is basically u to the negative 2 in there. So if I do integral with this, I am going to have, all right, so so I'm going to have my 52.8706. I'm going to wait. I'm going to do some bunch of calculations all at once is how I decided to do it. All right. And so this term right here, this is u to the negative 2. That, when I take its derivative, this is going to be u to the negative 1. And then I am going to have to divide by my new exponent, right? Because u to the negative 2, add 1, divide by the new exponent. All right, then that's going to be plus c, like this. And so, all right, now I am going to do two things simultaneously. I am going to plug and chug on this. Those negatives will just cancel, but I'm going to plug and chug on this, and I'm going to make a substitution of u in there. And so I'm going to get back to being as a function of time. All right, so this whole thing right here, when I calculate it, so this is going to be a little more than, it's going to be up in the 65 range, or about 66. But when I multiply that out, I'm going to get 65.8794, like so. All right, then I've got u to the negative 1. All right, so this right here, the 65.8788 is basically this number times this, knowing that the negative 1 is going to cancel. All right, I've got u to the negative first power. I'm going to write it like this. So what was u? Okay, let's go back up here. U was 1 plus this. So that's going to go down in the denominator. I will have 1 plus 2.4449 e to the negative 0.3277 t, like that. All right, and then plus my constant. All right, so now I have got myself an expression for this, and I'm going to use the initial conditions that they give us. And so let's go back and remind ourselves, what were the initial conditions? We're looking at the heights of these boys, and we're saying that, all right, age t, so if at birth there's an average height of 19.4 inches, all right, so that at birth, that is equals 0. So we're going to call that, so h of 0, and that's going to be kind of nice because basically when I plug in t equals 0, this whole thing is just going to be 1. So I'm going to end up with 65.8794 all over 1 plus 2.449. So I'm basically going to have 3.4449 in my denominator, and that plus c. All right, so take a look at that. Convince yourself that when you put the t in there, equals 0, that becomes 1. This becomes 1, so it's 1 times that, plus 1. All right, 3.4449. And we said that that was going to be equal to 19.4. That is in inches. All right, so plug and chug on here. And if you do this calculation, then let's see, what do I get for C? All right. Oh, for C, I get, okay, so I've got 65 divided by 3.5. And so my constant is going to end up being equal to about 0.3, be equal to 0.3. And so that's going to be what I'm going to add on there. All right, so we now have our total expression. It's this whole thing, right, plus 0.3 in there. And so now we have an expression, and we've nailed down what that constant is. We've got that. And so the only one more thing to do, and then we're going to call it here, and that is we want to know what is the height predicted by this model at age 8 in there. So that's basically plug and chug, 65.8794, all divided by 1 plus 2.4449, and then e to the negative 0.3277, and then that times 8 years, like so. And then we add on our 0.3. All right, and again, plug and chug, grab a calculator, and if got everything here, this is going to round off. I'll do it to 2 decimal places. So we are looking at about 56.22 inches and 8 years old. Okay, that seems to make some good sense. So 12 times 5, so 5 feet. 12 times 5 is 60 inches. So we're talking about a little under 5 feet. There. All right. I'm going to pause, end the recording.